Hello, how are you? My name is Mr. Rodriguez and today we'll be doing a revision session on forces and motion for paper 1 physics Edexcel GCSE higher. Throughout the session you will need to stop the video a few times in order for you to answer the questions. We'll stop the video, answer them on a paper and then check if your answers are correct. Please leave any comments if you got any questions about this session. So let's get started. Now you should be stopping the video and trying to answer these low stake test questions. Okay, so let's have a look. For the first question, name one thing which could affect thinking distance. Well, thinking distance is in close relation with reaction time. So anything that affects your reaction time will be affecting thinking distance. So those things could be drugs, alcohol, tiredness, age, and distractions. So any of those will get you a mark. Okay, now name one thing which could affect braking distance. This is only due to the road conditions and the car conditions. So it could be a condition of the tires, what else? Condition of the brakes and condition of the road. Okay. Name one safety feature which cars have to protect people if there is a crash. Well, there are three main ones. So all of them will try to reduce the force of the impact by increasing the time of the collision. So what can increase the time of the collision? So you could got airbags, you got seat belt, and you got the crumple zone. Don't worry, we will be covering all of this later. Okay. What are the units for acceleration? Well, acceleration is the change in speed over time, right? So what are the units for speed? Meters per second, and then because it's over time, it will be meters per second squared. So the units for acceleration are meters per second squared. What are the units of force? Newtons. That was an easy one. Okay, let's go to the next slide. Hey guys, so as I said, today we are covering topics 1 and 2, which corresponds with motion and forces for physics Edexcel higher. What do you know about topics 1 and 2? Let's start by adding the units for all of these numbers. Okay, so number 1, force, it's newtons. Second one, mass, is kg. Okay, it's not grams, it's kg. Acceleration, we did that in the LSD. Meters per second squared. Yeah. Speed is meters per second. Velocity is meters per second as well. Distance is just meters, and time is in seconds. Okay, well done. If you got all of them correct, let's move on to the next slide. Okay guys, so in physics we've got two different types of quantities. We've got scalar quantities and vector quantities. A scalar quantity will only have size or magnitude, but it will not have a specific direction. So for example, 4 meters. Okay, then vectors on the other hand will have size or magnitude and direction. It will have a specific direction. So in this case we've got an example, 4 meters north, because it has got a magnitude 4 meters, and a direction north. It will be a vector quantity. Okay, so in physics you will see that many measurements will have a scalar version and a vector version. Let's have a look at the first one. Displacement will have a scalar version. Displacement has got a direction, so therefore direction here, so therefore it will be a vector, and the scalar version is the distance. Okay, distance does not have a specific direction. Remember, the definition for displacement is the distance between the start point and the end point. So you could be covering lots of distance, but if you end up where you started, your displacement will be 0. Okay, then we've got 3 meters per second south. What could that be? We've got the scalar version, which is speed, 3 meters per second. Then what is the vector quantity for speed? That would be velocity. Okay, then weight, we got 50 newtons, and then the scalar version, which does not have a direction, will be the mass. Okay, now what is the direction of weight? It's always pointing towards the center of the earth. Okay, so it depends where you're sitting. So imagine that the object, this is a planet earth. Okay, then imagine that the person is over here, then the direction won't be down, it will be pointing towards the center of the earth. So be careful when you have to draw the vector arrows in your exam. Then some measurements are just either scalar or a vector. They don't have different versions. So for energy, we've got that this is scalar. Time, does it have a specific direction? No, it doesn't. It's also scalar. And force will always have a direction, so therefore it's a vector. Every single force, doesn't matter which one, is a vector. Okay, so we got our first exam question. It says, use the words from the box to complete the sentences below. Vectors have size and direction. Okay, guys, remember to stop the video whenever you want to answer the questions by yourself. I will also provide you with some extra exam questions on the mark scheme at the end of the video. Scalars have only size. What's another word for size that you might find in the exam? That's magnitude. Okay. Now we need to put a cross next to the option which has got two vectors. Is speed a vector? No, it's not. That's a scalar. Remember, the vector version of speed is velocity. Acceleration is a vector. Then we've got energy, it's a scalar. Time, scalar as well. Then force is a vector. It will always have a direction. Temperature, on the other hand, is a scalar. It doesn't have a direction, so the only possibility is the last one, velocity and displacement. Remember that displacement is the distance from the start to the end point, and velocity is a vector. It needs to have a specific direction. Okay? Okay, so let's just do a quick recap on mass and weight. This is a triangle that will help you answer the questions in case you don't know how to rearrange equations yet, which you should know by now. But if not, what can we do? So imagine you need to calculate the mass. How do you calculate it? You cover mass with your finger, okay, and then that will leave you with weight over gravitational field strength. Okay, same with for G, for gravitational field strength, you cover G with your hand, and that will leave you with W over M, so weight over mass. And then if you want to calculate the weight, you just need to do mass times gravitational field strength. Now let's have a look at the units. For mass, if you did this correctly in the starter, you should know that it's kg. Then for weight, it's newtons, because it's a force. Every single force is measured in newtons. And then G on Earth is 10, always 10 newtons per kilogram. Now I know that some of you might say, no, sir, it's 9.81. Well, in GCSEs, you are allowed to use 10, and that will make your calculation so much easier. Okay, let's solve these two questions. Remember to stop the video if you want to attempt them yourself. So we've got a car dealer that says that the car has a weight of 1,500 kg. Why is this statement incorrect? Well, people, when they use common language, they have misconceptions. They do not use physics language, right? So he's saying that the weight is 1,500 kg. So we know that the units for weight are newtons, it's not kilograms. So So therefore the statement is incorrect because the units for weight are newtons and not kg. Kg is only for mass. Okay? A different car has a mass of 1,200 kg. Now he's saying it correctly. Calculate the weight of the car. Now let's remember the triangle. We've got W at the top, then M times G. So really simple. We multiply the mass by 10, so 1,200 kg times 10 newtons per kilogram. Goes, and then the answer is 12,000 newtons. That would be it. Okay, so let's have a look at distance time graphs. Which letter represents an object which is stationary? Remember that in distance time graph, as the name indicates, we got distance versus time. We're representing distance and time. So for an object to be stationary, it must not move. The distance must not increase. The only letter that corresponds to that is B. So the object is stationary at B. Now, moving at a constant quick speed, so the fastest on the graph, that would be C. Okay? It's covering more distance in very little time, just 30 minutes. Okay? And then which object is traveling backwards? That would be D. Okay? So D is going back to the starting point. So that's it. If you want to carry out a calculation to calculate the speed, you just need to do the difference in distance divided by the difference in time. Please make sure that you do not use all of this distance because that would be wrong. Okay, so in the previous slide we could see that by calculating the gradient in a distance time graph we were calculating the speed. Now here is slightly different. When we calculate the gradient, so difference in velocity, final velocity minus initial velocity divided by the time, so change in y divided by change in x, we are calculating the acceleration. So final velocity minus initial velocity divided by time is equal to acceleration. Now there's one more thing that we can calculate, and that is the distance traveled. How do we calculate that? By using the area under the graph. So we want to calculate this first bit. We need to calculate all of this area, and that would be base times height and divided by 2 because it's a triangle. So base times height divided by 2. Initial velocity is 0, it goes up to 30, so that would be 30. Now the base is 2 seconds, so times 2 seconds, and then we divide it by 2, and that would be 30 meters of distance covered. Okay, so now let's have a look. When is the object stationary? When is the object not moving? The only place which is not moving is at 0, so that would be A. Then when is it moving at a constant speed? When is speed not changing? Over here at 30, from 2 seconds till 5 seconds, so that would be C. Now for the last one, when is the object accelerating? It's accelerating at a constant rate both in B and D. If it was not at a constant rate, it would look like a curve rather than a straight line. So now we have another exam question. Please stop the video if you want to attempt answering it yourself. For part P, we can see how the object is going from 0 to 30 in 50 seconds. So the car is changing its velocity over time, so therefore it is accelerating, and you're correct, it's at a constant rate. For Q, the car is traveling at a constant speed, it's not changing speed, it's going at 30 from 50 seconds to 150 seconds, so that's already done for us. Then for R, let's see. So for R, the car is going from 30 back to 0, so the car is decelerating. And then lastly, during S, the car is not moving from 250 seconds to 300 seconds, so the car is stationary or standing still. Okay, so let's talk about stopping distance now. The driver sees a deer on the road and brakes to a stop. The total distance traveled before the car stops can be split into two sections. What are these two sections? Section 1 and section 2. Stop the video and try to answer it yourself. Okay, so for section 1, that would be thinking distance. Thinking distance is defined as the distance covered by the car from when you see the danger until when you apply the brakes, and that's in relationship with your reaction time. So anything that affects your reaction time, like drugs, alcohol, tiredness, age, will affect your thinking distance. Then for section 2, that would be braking distance, and that it's only due to the car condition and the road condition. Okay, so as we said in the previous slide, the thinking distance starts when you detect the danger in the road, and it ends when you start braking, when your foot hits the brake. Now after that, it's just braking distance, and it's from when the brake is hit until when the car fully stops. So what conditions? I said road conditions and tire conditions, but how are these conditions affecting the braking distance? Well, if the road is slippery, so if it's got water or if it's icy, the grip of the wheels onto the road will not be good, so it will not have enough friction, and therefore the braking distance will be longer. Same thing with worn tires or worn brake pads, so all of those things you can mention in an exam question. Okay, so in summary, stopping distance is made out of thinking distance and braking distance. Let's have a look at the factors affecting stopping distance. I want you to create this table in your book, write down thinking distance and braking distance, and you need to put all of these words over here, you need to put them underneath the corresponding table. There will be one of them that you need to use twice. I'm not going to give you any other hints apart from that. And then as an extension, you can choose one of the factors and explain how it affects either thinking distance or braking distance. Okay, so let's have a look at the answer. So for the thinking distance, we've got distractions and mass of the car. For braking distance, then for thinking distance, we've got speed of the car, we've got drugs and alcohol, that will affect your reaction time, and therefore you will take longer to hit the brake, so your thinking distance will increase. The tiredness, if you're not rested well, then you will take longer to hit the brake as well, and it might take you longer to see the danger as well. Medication, certain medications are not recommended to use when you're driving. You can see that on the prospect of the medication. And speed of the car, obviously if you're going faster, then you will cover more distance in the same time, so your thinking distance will increase. So the one that applies for both, as you guessed, is speed of the car. Okay, speed of the car will affect the momentum. Remember that momentum is equal to the product of the mass times the velocity, and momentum is also a measurement of how difficult it is to stop the motion of an object. So the more momentum you have, the more difficult it will be for the car to come to a stop. So increasing the speed of the car will both increase thinking distance and braking distance. And the rest are road conditions. So if the road is slippery, the tires will not have a good grip and it will take longer to brake. Condition of the tires and the brakes, that will also increase the time for the car to come to a full stop. Okay, let's move on. As I mentioned in previous slides, thinking distance will depend on the reaction time of the person. So if they asked you to design an experiment on how to measure the reaction time, how would you do it in an easy way? Well, the way I did it in my school is with a meter ruler. Well, actually I was using half-meter rulers and hand, and that's it, nothing else. I didn't need any other equipment. Then I had a table already pre-made that correlated centimeters in the meter ruler and the reaction time. Okay, so let's say that 1 centimeter is a reaction time of 0.01 seconds, 2 centimeters 0.02 seconds, 3 centimeters 0.03 seconds, and so on. Now this is just as a reference. Obviously it might be other values, but just for you to have as a reference. So now, what is our independent variable? What are we changing in this experiment? Remember, independent variables, what we change, dependent variable, what we change, and that would be the person. Okay? Now, what is our dependent variable? What are we measuring? We're measuring the distance that the ruler travels down. Okay, control variables. What are we trying to keep the same? Well, we want the same person maybe from the ruler, same person releasing the ruler. And same ruler, same divisions, same ruler. Then another control variable, what could it be? Throw it at the same, from the same height. So release from same height. Now, as with every science experiment, how can we make our results more accurate? You cannot just say repeat 3 times, I will not get you a mark. You could say, for example, to increase accuracy, repeat 3 times and average. Okay, perfect. And let's move on. Okay, so this used to be the extra equations that you were given at the back of your paper. Now we're gonna try and attempt some questions that cover these equations. Okay, so let's have a look. Which equation do we need to use for the first question? Stop the video and try to find it yourself. Okay, so let's have a look by looking at the variables that we're given. We've got initial velocity over here, so vi, then final velocity vf, then we got distance of 10 meters, distance is x, and we need to calculate the acceleration. So the equation that links all of these variables together is final velocity squared minus initial velocity squared equals 2 times a times the distance traveled. Okay, so this is what we're trying to find, the acceleration. Let's have a look. Final velocity is 25, so 5 squared is 25, minus initial velocity 2 times 2, so 2 squared is 4, equals to 2 times the acceleration, which is what we need to calculate, times the distance traveled, which is 10 meters. Now, we can see that 21 is equal to 20 times a. Now, how do we rearrange this to calculate acceleration? You can do it in 2 different ways. Either you divide both sides by 20, or you send the 20 with the opposite symbol. Here, it's multiplying. You send it to the other side, you will send it dividing. It's the same result, okay? So 21 divided by 20 equals to the acceleration, which is 105. What are the units, guys? Remember, meters per second squared. Okay, so let's have a look at the second one. The car has a mass, so we've got mass here, of 3,500 kilograms. Just before it hits a wall, it has a velocity, we've got velocity here, of 4 meters per second. It comes to stop in 0.5 seconds, and that's time. So which of these equations will include all of these variables: mass, force, velocity, and time? Well, this equation is useful to calculate the force of an impact. And the force will be equal to the change in momentum, so final momentum minus initial momentum divided by the time. Now, anything that increases the time of the collision will reduce the force of the impact. Remember, if we increase time over here, the force will be reduced, okay? And that's the same function that seat belts, airbags, and crumple zones do. Back in the day, cars were built with iron instead of aluminium. Nowadays, most of them are built with aluminium, and aluminium can easily collapse. It can easily break, okay? So it crumples, and that will increase the time of the collision, successfully reducing the force of the impact. Back in the day, these cars made out of iron, they wouldn't break, but the people that were inside the car will most likely die if the car was going at a really high speed. And that doesn't happen as often nowadays, thanks to the crumple zones. So let's have a look. We need to calculate the force. So force is equal to final momentum. What is a final momentum? It's 0, okay? Now, the initial momentum, final momentum is after the collision. The initial momentum just before it hits the wall, it's 3,500 kg, that's the mass, times the velocity, which is 4. And then you need to divide all of this by 0.5 seconds. So our answer is 28,000 newtons. Okay? Now, you might have noticed that we've got a negative symbol over there. So actually the force will be negative. So what does it mean? It means that the force is going in the opposite direction as our original motion. So the force is coming towards us. Yeah? And that's it. Okay, so we have already covered this equation. This would be momentum. That's the mass. And that's the velocity. So, quick question. Is momentum a scalar or is it a vector? Remember, vectors, you have size and direction. Scalars only have size. Okay, so the unit for momentum will be the product of the mass and the velocity. What is the unit for mass? It's kg, right? And the unit for velocity is meters per second. So that's our units for momentum. Okay, so at the bottom, we've got the law of conservation of momentum. Law of conservation of momentum says that the total momentum before a collision is equal to the total momentum after a collision. And that means that momentum is always conserved. Okay? That's it. So, to my previous question before, is momentum scalar or a vector? The answer is it is vector. Okay? So it's the product of mass times velocity. Mass is a scalar, but velocity is a vector, remember. Velocity is speed in a specific direction. So momentum, as you can notice over here, it will always have a direction. So now I'm going to go through one example of what happens when two objects collide and stick together. We need to calculate the velocity of the objects after the collision. So let's start by calculating the individual momentums of both. So you've got momentum before equals momentum after. So we've got mv, 1, so m1v1 plus m2 v2 equals m3 v3. So mass of the first object, that would be 40, and then the velocity is 5, 40 times 5 plus 30 times minus 4 equals m3 v3. So 200 minus 120 equals m3 v3. So 80 will equal, where's the mass of the object now? Remember, we had 40 from the blue one, 30 from the other one, will be 70 kg, will be 70 times v3. So to calculate v3, we just need to do 80 divided by 70, which is 1.143. The units meters per second. Okay, so why is this momentum negative? Well, it's because it's going in the opposite direction. Remember, velocity is a vector, so it will also indicate the direction. In this case, the direction is indicated by the negative sign. The negative sign indicates that the object is moving from right to left, whereas the positive sign on the left side indicates that the object is moving from left to right. Okay, so this question came not so long ago in the official GCSEs. As I mentioned before, I'm a GCSE teacher and GCSE examiner for Edexcel, so I've marked this question quite a few times. Now, we need to show that the momentum of the bullet is about 5 kg/s, meters per second. So, we're going to calculate the momentum, really simple. We do momentum, always write the equation. Remember that you can get marks if you write the proper equation. Momentum equals mass times velocity. The mass is 0.03 times 170. That's about 5.1 meters per kg meters per second, which is about 5 kg meters per second. Now, for the last question, they tell us that the bullet collides with a wooden block and sticks in it. The bullet and the wooden block move off together. That's really important because that will imply that we need to add both masses together. One of the main misconceptions that most of the GCSE students had last year is that they were not adding the mass of the bullet to the mass of the wooden block. They completely forgot about it. So the results are quite similar because the bullet obviously is just 0.03 kg. So the result of the velocity doesn't change that much, but this is one of these questions where the range of velocities is not acceptable. You need to give the exact velocity. So how do we calculate this? Well, really simple. What is the momentum before the collision? 5 kilograms meters per second. That's the momentum of the bullet. Okay, so let's use the 5.1 actually, which is more accurate. So momentum of the bullet before collision. That's 5.1 kg meters per second. What is the momentum of the wooden block? Remember, guys, it's not moving. So if momentum is mass times velocity, and velocity is 0, what will be the momentum? 0 as well. So the momentum of the wooden block before the collision is 0. Now I'm going to write that momentum of the system after the collision. So I'm saying system because the bullet is now traveling with a wooden block. So you need to add both masses. Momentum after collision is equal to 0.83 kg times V2, which is what we're trying to calculate, right? So now the only thing you need to do is divide 5.1, which is momentum after. We're doing 5.1 equals 0.83 times V2. So 5.1 divided by, oh, sorry guys, I don't have space there. Let me, here it is. So we do 5.1 divided by 0.83, which is equal to, let's see, 5.1 divided by 0.83. That's 6.14 kg m/s. Okay guys, thank you so much, and please subscribe if you liked the lesson. See you soon. Bye bye.